Okay, so in this video, we're going to do the sum of a geometric sequence. Sum of geometric sequence. Okay, and this is another one of these beautiful ones of really nice algebra tricks that make the whole problem possible. It seems like something that should be impossible, but there's this like mind-blowing trick that just makes it so easy. So what is a geometric sequence? I'm going to do an example. I'm going to do my favorite example. The sequence 0.9, 0.09, 0.009, 0.0009, and so on. And for concreteness, let's stop at some number. Let's stop at 0.00. Let's fix a number of terms. So let's say there's 100 zeros, then a 9. So the first one has no zeros. The last one has 100 zeros. So there's 101 terms in the sequence. So 101 terms in the sequence. So here is A1, which is 0.9, and here is A101, which is 100 zeros and then a 9. Okay. And the question is, what is the sum? What is the sum? The sum is what? And it's going to be, what we're actually calculating. Of course, by the way decimal numbers work, I can tell you what the sum is going to be. It's going to be 0.999, and there's going to be 100 nines. Right? Because when you add 0.9 plus 0.09, you just get 2 nines, and then you add the third 9, and so on. So we know the answer already. This is going to be the answer. But I would like to express the answer in a way that is more useful for other calculations and that works in general. So here's how I'm going to do it. So we're going to find this as the answer, but we're going to express it in a different way that makes it clear what's going on. I'm going to write S for the sum. So S is equal to this number, 0.9 plus 0.09 plus 0.09, all the way up to 100 zeros, 9. Okay, that's S. And just like before in the arithmetic sequence, summing the arithmetic sequence, we're going to do manipulations to this equation to get a new equation. And it's going to be set up so that it kind of gels with this equation in a nice way where we can do something and get them to work. So if you remember, for the arithmetic sequence, we wrote the equation backwards, right? That was this trick. We started with the first line for S, we wrote it backwards, still S, then we added them together. We're going to do something almost like that in here for the geometric sequence, the geometric sum. What is it going to be? So here's the trick. I'm going to multiply the equation by 0.9. Multiply it by 0.9. And I'm not going to multiply by 0.9. I'm going to multiply by 1/10. 1/10. So 1/10 S is what? Well, 1/10 S, the first term would be 0.09, right? Because you take 0.9 and you multiply it by a tenth, you get 0.09. The next term would be 0.009. Take 0.09, you multiply by tenth. So I'm just going term by term and multiplying them all by 0.009. Okay, and if you do it that way, you get at the last term, you have something with 101 zeros. 101 zeros. 9. Okay, and before in the arithmetic sequence, there was a nice property of every column. Every column had a nice thing going on that we could exploit. Do these columns have a nice thing? No, those are two different numbers. I don't know. No pattern. These are two different numbers. So what are we going to do? Here is the big secret of this one. It's not that every column has something. Everything is shifted over by 1. Everything is shifted over by 1. And I'm going to use the magic of computers to select everything and show you what happens when we shift this over by 1 term. Aha! Look at that. Okay, let me fix my 100 zeros indicator. Went away. 100 zeros. That went away. But now that I've shifted everything over by 1, of course, shifting things over by 1 does not change the sum. It's a totally true equation. But now there is a nice pattern in every column. There is a nice pattern in every column. The same number appears in every single column, except, okay, there's 2 exceptions. There's the first column is different, and the last column is different. Okay? So the first and the last column are different, but other than that, it's the same exact thing in every column. And of course, the reason it works is because in the arithmetic sequence, you multiply by a tenth to go from one number to the next number. A tenth was that R value of multiplying. And so if I take the whole equation and multiply it by a tenth, of course it's going to all shift over. Like it was exactly set up to work like this. So it'll always do this for any geometric sequence. I might have said arithmetic a minute ago. I meant geometric. Okay. So how do we finally finish the problem? We're going to do the same trick we did before. Last time we added the two columns because there was a nice pattern when you add them. If it's the same number, there's a nice pattern when you subtract them. So I'm going to subtract to the equations. Subtract. So maybe I'll draw a big minus sign right there. First equation minus the second equation. So on the left-hand side, it says s minus 1/10 s. First one minus the second one, s minus 1/10 s. What does it say on this side of the equation? Well, 0.9 minus 0, right? There's a 0 here. 0.9 minus 0 is 0.9. That's the first column is some kind of funny exception. But the second column, 0.09 minus 0.09 is 0, right? Same number. And the third number is 0. And the fourth number will be 0. And the fifth number will be 0. And there's going to be all these zeros 100 times in a row, all the way up to the last term, which is the other exception. In the other exception, we're doing 0, right? You can think of this as plus 0, minus 0.0009 with 101 zeros. So plus 0.009 with 101 zeros. Okay. And there you go. Look, we have a super good equation that we have simplified quite a bit for s minus 1/10 s. And that equation is s minus 1/10 s. You start with a whole s, you subtract off a tenth, you're left with 9/10 s on the left-hand side. On the right-hand side, you have 0.9 minus 0.0, 101 zeros, 9, that number. And if I just rearrange the equation, I'm going to take the whole equation and multiply it by 10 ninths, or effectively move this 9 over 10 to the other side of the equation. You get s is 10 ninths times 0.9 minus 0.009, 101 zeros, 9. And there you go. That's the answer. That's what s is. You can simplify it a bit. 0.9 is the same thing as 9/10. And this thing, 101 zeros, is the same thing in sort of scientific notation. This is 9 times 10 to the minus 101. 101 zeros, and then a 9. Or is it to the minus 102? I guess it's to the minus 102. Okay. So if you write that in scientific notation, it looks like that. And now I can distribute this 10 over 9 in. Look at this. S is 10 over 9 times 9 over 10. Beautiful number 1. The 9 here cancels with the 9 there, and you're left with minus 10 to the minus 101. So S is equal to 1. It's the number 1, exactly 1, minus 10 to the minus 101. 10 to the minus 101 is the number 0.0, 101 zeros, 1, right? That's what, maybe it's 102 zeros. No, 100 zeros. 100 zeros. Okay, great. Yeah, okay. 100 zeros. So it's 1 minus 100 zeros 1, also known as 0.999 100 nines, right? Which is what we knew. We knew the answer already when we started. But look, we have expressed the answer in this really nice way. It's 1 minus a tiny bit. 1 minus a tiny bit. And the strategy we used will work for any number of terms, right? So in general, the sum of the first n terms is, what is it? It's going to be 1 minus 10 to the minus n, right? The number of terms in this problem was 101 terms, and the answer was 1 minus 10 to the 101. In general, you do it with n terms. It's this. And this is the reason, this formula, s equals 1 minus 10 to the minus n, is the reason that people say 0.99 repeating equals 1 exactly. So if you let n get bigger and bigger, if you think of the number of terms in the sequence that you're adding on, as that gets bigger and bigger, you have this thing, 10 to the minus n, and it's getting exponentially small. As n gets bigger and bigger, this 10 to the minus n gets so tiny that this thing gets really close to 0. Gets close to 0. And that is why the 0.99 repeating forever is exactly equal to 1. The only thing that is left over is this 1 in the front. So in general, it's 1 minus a tiny bit, and that tiny bit gets so close to 0 that if you were to do it infinitely many times, it's equal to 1. So formally, we say the limit is equal to 1. We're going to do limits exactly in the next section. On the first class back from the break, we're going to do limits. Let me recap what I just did here. I did it all for this special case of 0.99. You can do it in general. And so let me give you the general formula. The general formula is also given in the notes if you want to follow along in on page 342. Result 38 is what we're doing. But we're finding this formula for this sum. The sum of a plus a times r plus a times r squared plus ... plus a times r to the n minus 1. And this is the sum of n terms of a geometric series where a0 is a, the first term is a, not a0, a1. a1 is a, and the common ratio is r. Common ratio is r. So a0 is a, and then it goes ar squared, and so on. So this is the sum we want to find. R times the sum shifts everything over by 1. So if you take a, you multiply it by r, you get ar. If you take ar and you multiply it by r, you get ar squared. And you do this a whole bunch of times. The last term, so there's going to be an ar n to the minus 1 from the last term over here. This term is going to become ar to the n with no minus 1 because you multiplied it by r. So everything gets shifted over by 1. That is exactly what we did before with 0.9. All the 0.9s getting shifted over by 1. And I've written it this way. R times s is this thing, and now the columns are aligned. Now I subtract the two equations. So subtract the two equations. You get s minus r times s on the left-hand side. What do you get on the right-hand side? This first column is an exception. You just get a from the first column. All the other columns, this column and this column and this column, all the other columns give 0. So plus 0, because they're the same term and we're subtracting them. Subtract them all. The last column is the other exception. So there's another exception in this column. There is nothing over here, plus 0 if you want this term. Over here, there's nothing written, plus 0. So when we subtract, we get minus ar to the n. Okay. Perfectly nice equation with only 4 things in it. S times minus r times s is equal to a minus ar to the n. So if you just factor out, this is a 1 minus r times s is equal to a minus ar to the n. In other words, s is a minus ar to the n, 1 minus r. You can also factor out an a if you want. A times 1 minus r to the n divided by 1 minus r, which is exactly the formula in result 38. So if you want to check out in the notes, this is the answer. We did an example already where a was 0.9 and r was 0.1, also known as a tenth. That was the example we just did, the 0.99s. Let's do one more example. Let's do this one. Let's do, this is a fun one. Let's do 1 plus 2 plus 4 plus 8 plus 16. What is that? So in this example, r is 2. R is 2 because you multiply every term to get to the next term. You're multiplying by 2. 1 to 2 is multiplying by 2. 2 to 4 multiplying by 2, and so on. And a is equal to 1. A equals 1. The first term is 1. So what does the formula say? The sum is 1, a, times 1 minus r to the n. R is 2, so 2 to the n, divided by 1 minus 2. 1 minus 2. Okay, 1 minus 2 is pretty easy. That's a negative 1. So something divided by negative 1. 1 minus 2 to the n. Oh, I got to know what n is. N here is the number of terms, right? N is the number of terms. What is n? 1, 2, 3, 4, 5. 5 terms. 5 terms. 2 to the 5 is 32. 32. So you get 31. 1 minus 32 is negative 31. Divided by negative 1. The negative signs cancel. It's just 31. So the answer is, this is 31. 31, that's the answer. So in general, it's always the sum of powers of 2 is always the next power of 2 minus 1. Just 1 less than the next power of 2, just like we saw over here. Okay, so that's how you do the sum of a geometric sequence, which is covered later in the notes, but this is how it actually happens.